welcome back. So, we shall now be moving on with the detailed discussion on various aspects of computer architecture and organization. As we know that typically these digital circuits work on binary number system, which can ultimately be mapped to some tiny electronic switches. So, in this lecture typically we will be considering this number representation in computer systems. So, number systems, we all are accustomed with the so called decimal number system. So, in decimal number system we represent 10 digits 0 to 9, and every digit position has a weight which is a power of 10, like base or the radix is 10. Let us take an example, 234. So, it can be represented, the weighted representation can be given as like this, 4 into 10 to the power 0, this is in the unit position, then 3 into 10 to the power 1, 10th position, and 2 into 10 to the power 2, 100th position, and then we get this number 234. Similarly, we can also represent both integer part and this fractional part, where the integer part, the number starts from, we multiply this number with 10 to the power 0, 10 to the power 1 and 10 to the power 2, and here we start with minus 1. So, we multiply 6 into 10 to the power minus 1, 7 into 10 to the power minus 2 and so on. Coming to binary number system. So, in binary number system we all know we have 2 digits 0 and 1, and every digit position has a weight that is power of 2. In decimal number system we have power of 10 and here we have power of 2. So, the base or the radix here is 2. Let us see how we can represent a binary number. So, 110. 110 is this number 0 will be multiplied with 2 to the power 0. The next number will be multiplied with 2 to the power 1 and the next will be multiplied with 2 to the power 2. So, this is the weighted representation of this number, and if you calculate what is coming, this is 4, this is 2, this is 0. So, this is 6. Similarly, we can also represent a fractional part. So, 101.01, it can be represented. So, this will be 2 to the power 0, this will be 2 to the power 1 and this will be 2 to the power 2. Same way, so we have done 1 multiplied by 2 to the power 0, 0 multiplied by 2 to the power 1 and so on. And again in the fractional part, in the same way we will be multiplying with 2 to the power minus 1, 2 to the power minus 2 and so on. So, this will be 0 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 and so on, if there are other numbers. Now, let us see some conversions. So, there are many conversion, binary to decimal, decimal to binary, binary to hexadecimal, hexadecimal to binary. So, we will be looking into all those things. So, when we are doing binary to decimal conversion, each digit position of a binary number has a weight, and that weight is some power of 2. If it is 1 in the last digit, then 1 into 2 to the power 0 and separate, and like that all others will be having some power of 2. So, a binary number can be represented as like this. This is the integer part and this is the fractional part. The integer part starts from B0, B1 to Bn minus 1 and the fractional part B minus 1, B minus 2 to B minus m, where Bi are the binary digits. So, these are the binary digits. So, what will be the corresponding value in decimal? So, the corresponding value in decimal will be all these digits, all these binary digits multiplied by 2 to the power I. So, if this digit is B0, then B0 into 2 to the power 0. If it is B1, then it will be B1 into 2 to the power 1 and so on. And here also B minus 1 into 2 to the power minus 1 plus B minus 2 into 2 to the power minus 2 and so on till B minus m. So, the corresponding value in decimal can be represented by this summation of I equals to minus m to n minus 1 bi 2 to the power minus I. Let us take some examples which will make this clear. So, we have a number 101011. This is a binary number. How we can convert it into a decimal number? So, we start with multiplying 1 with 2 to the power 0, because this is 2 to the power 0, 2 to the power 1, 2, 3, 4 and 5. So, 2 to the power 0, 2 to the power 1, 2, 3, 4 and 5 and we sum it all. So, we get 43 in decimal. Similarly, if we have a fractional part, how we can convert it? We have to multiply this with 2 to the power minus 1, 0 with 2 to the power minus 1, because it will start from minus 1, minus 2, minus 3 and minus 4. So, I will be multiplying with 0 into 2 to the power minus 1 plus 1 into 2 to the power minus 2 plus 0 into 2 to the power minus 3 and 1 into 2 to the power minus 4, which comes down to 0.3125 in decimal. Similarly, if we have a both integer part and fractional part, in the same way we can consider the first part as like this and the next part like this, and finally we get a value like this. Now, let us consider decimal to binary conversion. So, we have seen binary to decimal conversion. Now, we will be seeing decimal to binary conversion. Consider the integer and fractional part separately. Here we have to consider the integer and fractional part separately. Let us see how. So, what we do for the integer part? For the integer part, we repeatedly divide the given number by 2 and we go on accumulating the remainders until the number becomes 0. So, let us take an example. So, here we can see that the number is 15. What we say that we repeatedly divide the given number by 2. So, we are dividing the given number by 2, we are getting a quotient and we are getting a remainder. So, and what we are doing? We are going on accumulating the remainder, that is here it is 1. Again we do it, we get here 3 and the remainder becomes 1. Again we divide it and we get the remainder as 1 and the quotient as 1 as well. And what we do finally? We arrange it in reverse order. So, in reverse order when we arrange, this 15 in decimal is now converted to 1111 in binary. So, here this is what it has been said, that for the integer part we repeatedly divide the given number by 2 and we accumulate the remainder until the number becomes 0 and then we arrange it in reverse order, the way just now I have shown. Next, for the fractional part. For the fractional part, what we do? We repeatedly multiply the given fraction by 2 and then we accumulate the integer part. See, the integer part will be 0 or 1, we accumulate that. If the integer part is 1, we chop it off. And then finally, while arranging, we will be arranging the order the integer parts comes in the order. In that order only we will arrange the part. So, now let us see this with an example again. Let us say we have taken 0.25. So, 0.25 we multiply it by 2 and we get 0.50. So, here 0 is accumulated, this is the integer part which is 0. Next, again we take the fractional part, we do not do anything with this part. So, we take the fractional part, this fractional part again we multiply it by 2 and what we get? We get 1.00, where we get this fractional this integer part as 1. So, here we can say that 0.25 in decimal can be represented as 0.01. So, this point remains and what we got is 01. We are not writing this in reverse order, rather we are writing it as 0101. So, this is the decimal, this is the binary representation of this particular decimal fractional part. This is how we do it, and we can continue doing it because it is not necessary that we will get 00. We can get any number. So, we can do it for some number of time and we get the result. Now, the examples I have already given. So, let us see some more examples. Here in the same way, 239 in decimal can be converted into this fashion into binary, where we get 1110 1111. We write it in reverse order. So, 239 in decimal can be converted to 1110 1111 in binary. Similar way, let us take another example which is 64. We go on dividing with the number by 2 and we accumulate the remainder, and finally, what we got is 1 0 0 0 0 0 0 in binary. Let us take some example with the fractional part. So, here we see that 0.634 in 0.634 in decimal, how we can convert it into binary. So, same way we multiply it by 2 and we keep the integer part, and then we take the fractional part again and keep on multiplying with 2, and again after multiplying it we keep the integer part, and again with this fractional part we multiply it again with 2 and keep on doing it. Let us say we have done it till 1, 2, 3, 4 and 5 times, and we write it in this order. So, the value will be 0.10100, and if you want to do it for some more, you can also do that. So, this is how we can convert a fractional decimal part to binary. Similarly, we can take an example of a number which is having both integer part and fractional part. So, the integer part can be converted and it is represented by this, and the fractional part is converted and it is represented by this, and finally, you can write the answer in this fashion. Now, coming to hexadecimal number system. Now, why do we require hexadecimal number system? Now, let us say you have to represent a big number, 32-bit number or a 62-bit number. So, if you have to represent a 62-bit number in binary, you have to represent it as 0, 1, 0, 1 up to 64-bit, or if it is a 32-bit number, then you have to write that 0, 1, 0, 1 whatever is the number till 32-bit. So, it will be really very long. So, hexadecimal number system is a compact way to represent binary numbers. This is an efficient way where what we do basically we group the 4 binary digits and they are represented by a hexadecimal digit. And what are the hexadecimal digits? The hexadecimal digits are 0 to 9 and A to F. 0 to 9 we already know, and starting from 10 is represented as A, 11 is represented as B, 12 as C, 13 as D, 14 as E and 15 as F. So, we have these representations starting from 0 to F in hexadecimal number. So, a group of 4 numbers, if we encounter a group of these 4 numbers, we will replace with a single digit, that is 0. If we encounter 1010, we will replace this with the number A, and this is an efficient way because we do not have to write that 32-bit or 64-bit, rather we can write it just this one single digit to represent 4-4-bit. So, if we have to represent a 32-bit number, let us say my 32-bit number is 'So, this is a 32-bit number. We have 4, 8, 12, 16, 20, then 24, 28 and 32. So, this 32-bit number can be represented by only 8-bit. How? Because 1010, what is 1010? 1010 is A, 0000 is 0, 0001 is 1, 0010 is 2, this is 8, this is 9, this is 0, this is 1. So, this entire number A01289001 is a hexadecimal representation of this 32-bit number. So, we will move on. So, let us see how we can convert this binary to hexadecimal conversion. So, for here also we have two things, for the integer part what we do and for the fractional part what we do. So, for the integer part we scan the binary number from right to left, and then we translate each group of 4 bits into the corresponding hexadecimal digit, and if required we add leading zeros. That means, if it is required that we need to add some more bits to make it a group of 4, then we can add those bits. So, for the fractional part what we do? We scan the binary number from left to right. So, there is a difference between your integer part and your fractional part. In the integer part we are doing from right to left, and in the fractional part we are doing from left to right. And what we do? We translate each group of 4 bits into the corresponding hexadecimal digit that I have already shown you. And for doing so, if it is required, then what we do? We add trailing zeros into it. Let us take some more examples. So, let us say we have a number which is represented in binary 1010. So, we group this from right to left. So, first we group this 4 bit, next 4 bit, then next 4 bit, and then we find out that we have a group of 3 groups having 4 bits. So, what is 1011? It is B. What is 0100? It is 4 in hexadecimal, and 0011 is 3. So, we have converted a binary number into hexadecimal representation. Similarly, here you see you do not have a group of 4. So, what you have to do? You have to add some zeros in the beginning. So, here we group it 4, here also we group it 4, but here we cannot group it 4. So, you add 2 more zeros. So, 2 leading zeros are added to make it 0010, which is equivalent to 2. 1010 is A and 001 is 1. Similarly, for the fractional part, we scan from left to right. So, scanning this from left to right, so we have to group into 4 bits. So, this is the first 4 bits and this is the next 4 bits. To make it 4, we have to add a trailing 0. So, a trailing 0 is added to make it a group of 4 bits. So, this 1000 is 8 and 0100 is 4, which in hexadecimal. Similarly, for this is the integer part and this is the fractional part. For the integer part, we have to add a leading 0, which makes it 0101, so which is 5. And then for this, we have to add a trailing 0. So, if we add a trailing 0, this will make it as 5 and this is E. So, this is how we convert a binary number into hexadecimal number for simple representing it in a compact fashion. Now, in a similar way, we can also translate or convert a hexadecimal to binary conversion. So, we can convert a number from hexadecimal number to a binary number. Translate every hexadecimal digit into its 4 binary digit. So, let us see this same example where we have already done from a binary representation. This is the binary representation and this is the hexadecimal representation. So, now what we are saying, how we can convert from hexadecimal to binary. In the same way, now here these are all binary, we have grouped it into 4 groups and then we have converted. In the same way, if you want to convert any binary digit, let us say A, 1 and 2 in hexadecimal. So, what you have to do? You have to convert each of this into 4 bits. A can be represented as 1010, 1 can be represented as 0, 0, 0 and 1, and 2 can be represented as 0, 0, 1, 0. So, this is A, this is 1 and this is 2. This is in decimal. So, this is how it is converted here. Same way, 3A5 is converted, this is 3, this is A, this is 5. Similarly, 12.3D, this is 1 and this is 2 and this is 3 and this is D. And in same way, 1 and 8 can be 0001 and 8 is 1008. So, how are hexadecimal numbers written? So, like we have to represent a number as hexadecimal, otherwise it will be difficult for the computer to understand. So, to do that, you can either add a suffix h or you can use the prefix 0, 0x. So, this here we are representing this 2a is a hexadecimal number where h is added as a suffix, and here 2ab4 is a hexadecimal number. How many bit hexadecimal number? This is a 16-bit hexadecimal number and it is added with a prefix 0x. And this is how many bit hexadecimal number? This is a 32-bit hexadecimal number with all ones. So, it is represented as F, 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 F and F. Now, how do we use unsigned binary numbers? A n-bit binary number can have 2 to the power n distinct combination. So, for an n-bit we have 2 to the power n distinct combination. For example, if you consider n equals to 3, so we will have 2 to the power 3 combination. So, 2 to the power 3 combination, what all are those combination? It starts from 0 to 2 to the power n minus 1. So, the first is 0 0 0, next is 0 0 1, 0 1 0, 0 1 1 and so on till 7. So, it is represented from 0 to 2 to the power n, here it is 2 to the power 3 minus 1, that is 7. So, similarly, for an 8-bit it will be 0 to 2 to the power 8 minus 1, that is 0 to 255. For a 16-bit it is 0 to 2 to the power 16 minus 1, for a 32-bit this much, and for a 62-bit and so on. So, a n-bit binary integer can be represented like this, and the equivalent unsigned decimal number is represented by this. It is multiplied by 2 to the power 0. So, each digit position has a weight, that is some power of 2. Now, let us come to signed integer representation. So, in signed integer representation, how do we represent negative numbers? How do we represent both positive and negative numbers? So, here the question arises how to represent the sign bit. There are 3 approaches that are followed. One is sign magnitude representation, another is 1's complement representation and another is 2's complement representation. First come to sign magnitude representation. So, in a sign magnitude representation, for an n-bit number representation, the most significant bit indicates the sign. So, if the most significant bit is 0, then we say it is a positive number. If it is 1, it is a negative number, and the remaining n minus 1 bits represent the magnitude of that number. So, for an n-bit number, what will be the range that can be represented? It is minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So, these many bits will represent the magnitude, and the last bit will be the sign bit, that is the most significant bit used to represent as sign. So, let us see this for a 4-bit number. So, for a 4-bit number, you can see the range is starting from minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. For n equals to 4, if you put this in the place of n 4, so you will get minus 2 to the power 3 minus 1 to plus 2 to the power 3 minus 1. So, we can represent minus 7 to plus 7. So, let us see how we can represent minus 7 to plus 7. So, 0 will be same as 0. So, all the till 0 to 7, it is the same as how do we represent it, and starting from this is minus 0, because the first bit represent the sign and this is the magnitude, this is the magnitude of 0, this is the magnitude of 0, and 0 represent plus 0 and this represent minus 0. And then we have minus 1, minus 2. So, this represent the magnitude and this represent the sign. So, this is how we can represent the set of numbers for n equals to 4 using sign magnitude representation. So, these are all the magnitude and this is the sign of the number. Now, what is the problem here? The problem here is that you see you have 2 representation of 0. So, you have 2 representation of 0. you have minus 0 and you have plus 0. So, this is one of the demerit of this method. We have two different representation for 0. Let us move on with another representation, that is 1's complement representation. So, the basic idea here is positive numbers are represented exactly in sign magnitude form, and for the negative numbers these are represented in 1's complement. So, what is 1's complement? By 1's complement of a number, each number, if it is 1, it will be converted to 0. If it is 0, it will be converted to 1. And the MSB will indicate the sign of the number. For a positive number, it will be 0. For a negative number, it will be 1. So, this is the representation for n equals to 4. So, in the same way, from 0 to 7, it will be the same as sign magnitude, and starting from minus 7, the representation is different. So, let us take the representation of minus 4. How do you represent 4? We represent 4 as 0, 1, 0, 0. So, this is 4, 0, 1, 0, 0. So, the minus 4 is represented using 1's complement. So, we do 1's complement of this, which is nothing but this 0 becomes 1, this 1 becomes 0 and this becomes 1, 1. So, this is 1, 0, 1, 1. This is how we represent. But here also the same problem exists. We have two representation of 0 and minus 0. So, here also the range of numbers that can be represented in 1's complement is plus 2 to the power n minus 1 to minus 2 to the power n minus 1 minus 1. But the problem here is we have two representation of plus 0 and minus 0. But there are few advantages, that is, using 1's complement, subtraction can be done using addition and it leads to substantial saving in circuitry. So, you will be looking into all these things in detail in the arithmetic and logic unit. So, for now you understand that we have few representation through which we can also represent negative numbers, and in 1's complement and in sign magnitude, in both the representation we have two different representation of 0, minus 0 and plus 0, that is a demerit. And what is the advantage of 1's complement is that for subtraction can be done using addition itself. In detail it will be taught in arithmetic and logic unit. Let us move on and let us see 2's complement representation. Here the positive numbers are represented exactly the way as sign magnitude form, but the negative numbers are represented in 2's complement form. By 2's complement, what we mean? Firstly, we do 1's complement and then what we do? We add 1 to the resulting number. So, this is the 2's complement representation. So, we have 1's complement of a number, then we add 1 to it and we get the resulting number. Here also the MSB will indicate the sign of a number, 0 for positive, 1 for negative. So, this is the representation for n equals to 4. Now, we see that 0 to 7 is same. Now, minus 8, how do we represent? We are representing minus 8, minus 7 in 2's complement. Let us take the same example of minus 4. So, how do you represent 4? It is 0, 1, 0, 0. Then we take the 1's complement of this number. 1's complement of this number is 1, 0, 1, 1. This is 1, 0, 1, 1 and then we add 1 to it. Once we add 1 to it, it becomes 1, 1, 0, 0. So, you see here this is the magnitude that we get. So, this is how we can represent a negative number in 2's complement, and the most advantage thing is that here there is only single representation of 0. We do not have something minus 0 here. So, 0 is represented 1. So, what is the range of number that we can here? 1 more than the previous one. So, the range of numbers that can be represented in 2's complement is plus 2 to the power n minus 1 and the minimum number is 1 more. So, earlier it was minus 2 to the power n minus 1 minus 1, that will be plus 1 because we can represent one more, that is it is 2 to the power n minus 1. Advantage, we have a unique representation of 0. Subtraction can be done using addition and it leads to substantial saving in circuitry. Almost all computers of today use 2's complement representation for storing negative numbers. Now, let us also see some more features of 2's complement which will be necessary for your further units. It represents a weighted number representation where MSB having the weight minus 2 to the power n minus 1. So, what does it represent? It represents that all these numbers will have 2 to the power 0, 2 to the power 1, 2 to the power n minus 2, but the last one, the magnitude will be minus 2 to the power n minus 1. So, let us see this. So, how we can represent minus 20 in 2's complement? So, minus 20 in 2's complement can be represented by, this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3, 4 and minus 2 to the power 5. So, we calculate this minus 2 to the power 5 plus 2 to the power 3 and we get minus 20. So, any negative number which we represent using 2's complement, the most significant bit will have 1. Now, let us add an extra 1 to it and let us see that whether this changes or not. So, we added 1 more in the most significant bit and let us calculate it once more. So, this will become minus 2 to the power 6 and all others will become 2 to the power 5 plus 2 to the power 3 plus 2 to the power 2. So, now this is how we can represent, which is again coming minus 20. So, even if you add the number of ones in the beginning, this will not change, this will be minus 20. So, even if you add one more 1 into it, this will not change. This will be represented as minus 2 to the power 7 plus 2 to the power 6 and this will remain as minus 20. So, this is what we call sign extension in 2's complement. So, if you also extend this sign digit more, then also this value will remain. Now, what happens if we shift left by k position with 0 padding? We are shifting left and with 0 padding. What it does? It multiplies the number by 2 to the power k. So, we can take an example where this is the number. What we say? We shift left. So, we are shifting it left. So, this number is shifted to left by 2. So, we will shift it once and we shift it once more. If you shift it 2 times, it will become 0 1 0 0 1 1 0 0 and this is equivalent to plus 76. Basically, we have multiplied by 2 to the power 2, that is 4. Similarly, if this is minus 29, we shift left by 2 and we get minus 116. So, shifting left meaning multiplication by 2. Now, we will also see shift right by k positions with sign bit padding. What will happen? Divides the number by 2 to the power k. Let us take an example. So, this example is where we shift right by k position and then what is happening? So, here you have a number plus 22. Once we divide by 2, we will get 11. Again we divide it by 2, we will get 5. Similarly, minus 28. So, let us take this example of minus 28 here. So, minus 28 can be represented as 1110 0100 in 8 bits, and then we do an arithmetic right shift. When we do an arithmetic right shift, the whatever value is the most significant bit that comes here, and all other bits are shifted 1111 position. See, that is what we have done. So, all other bits are shifted to 1111 position, and then this bit comes in the most significant bit, and this representation is nothing but minus 14. Similarly, we are doing arithmetic shift right once more, and same 1 bit comes in this position. So, 1 is coming here and all other bit are getting shift to 111 position to the right. So, we get 11110001. This is equivalent to minus 7. So, this is how we perform shift right by k position with sign bit, and which actually divides the number by 2 to the power k. Now, this sign bit can be copied as many times as required. I have already shown you this in the beginning to extend the size of the number this is called sign extension. So, this is the number 8-bit number which is plus 47. Sign extension to 32-bit, you add as many number as 0 as possible, it will still remain plus 47. Similarly, a negative number which is minus 93, I have shown you with an example that if you add as many 1 in the beginning to extend it to 32-bit, the number will remain as minus 93 only. So, we can see that in 2's complement how we can represent it and how we can do sign extension. So, we came to the end of lecture 6, where we briefly talked about number systems such that it will be easy for you to get into how instructions are now will get executed in next course of lectures. Thank you.